The assembler I've been writing for my homebrew 8-bit CPU currently doesn't have any support for jump labels, which is very annoying. And so whenever we're doing a relative jump, we have to manually compute the jump offset in bytes. For example, in the test program for the CPU flags, there's this loop here. And this required us to manually compute the jump offset to get back to the beginning of the loop here and basically run through this part of the program multiple times. But whenever I add something to the loop body, I would have to go back in and recompute that jump offset. Because with this additional instruction in the loop body, the jump offset would no longer be -16, it would now be -18 because we have to jump further back. And this hasn't only come up here in this flags test program. When testing the bit shifts in the ALU, we had this loop at the end of the test program which also had to encode a jump offset manually. And just by looking at the code like this, it's not entirely clear where this relative jump actually jumps to. We can go and count the lines, but it would be nice if this would actually be evident in the program here. And in this general test program for the assembler, we also have a few of these relative jumps. For example, here in line 13, we have a jump relative that jumps forward by 18 bytes, which happens to land at the hex address 20, which is where the rest of the program then actually is positioned. And the way assemblers usually deal with this is they allow you to specify labels like this, and then use that label in relative jumps and other places in the program to compute jump offsets. So instead of hard coding that plus 18 byte jump, you just specify what the jump target label should be. And then when the assembler does its thing and it encodes the instructions, it will actually compute the jump offset for you. And this is exactly what I want to add to my assembler today. And we have to do two things. We have to allow the user to specify these labels in the program, which are kind of a special directive, which will just track the address of that specific label. And we have to allow the user to use these labels in the place where you would normally write a jump offset. So let me start with the label declarations. I want to be able to use just regular identifiers like add or start, but also integer labels, which are pretty common in assemblers. They allow you to have multiple labels with the same number defined, and you would be able to specify which one of the integer labels you mean when you use them. So let's see how we can add this to the assembler. The assembler has no idea how the labels work yet, so it just thinks that we mean a add instruction here, and then it complains about a missing register. So let's go into the assembler source code and let's add label parsing. Before we actually consider all the different instructions that we understand, let's first check if we're currently at a label specification. And a label is any sequence of lowercase and uppercase letters, numbers, and probably underscores, followed by a colon. And I think we need a new operand kind that captures the name of the label. And we'll also declare a new directive opcode, which we'll just call label, which is a label definition in the program. So let me add that operand kind. And let me also add the label directive under opcodes. Let's see what happens if we run this. Pretty cool, that already seems to work. We parse the instructions properly, and then the assembler complains about the fact that this label directive here is not an encodable instruction. We haven't specified how this should be encoded. But this is an easy fix. There's nothing to encode for a label. It's just a placeholder in the program text that doesn't really appear in the output assembly in the actual instruction byte stream. So we'll do the same thing as the org directive. We'll just ignore the directive when we produce the bytes for the final binary. All right, and that now already works. And as you can see here, the labels appear as these directive instructions. They're assigned an address here on the left, and then they're printed in this generic form because we haven't specified how these labels should be printed in the assembly text. Let me actually go and quickly fix the printing such that the labels appear in a more human-readable form. So if I run the assembler again, the labels appear as you would expect. But weirdly, if you look at the addresses of the labels, it looks like the labels influence the address. So the add label is placed at hex 20, which is what we would expect after the origin directive. But then the label 1 is placed at hex 22 and the label start at hex 24. So clearly when laying out the instructions in the program, the assembler just assumes that these labels consume the usual 2 bytes of encoding space. So here when we lay out the individual instructions, the origin directive has a special treatment. And then all other instructions will basically use the current address and then also increment the current address by 2. But for our label directives, we just want to set the address of the label to whatever the current address in the binary is, but then we don't want to do this incrementing by 2 because the label itself doesn't use up any space in the output. And now when I run this again, you can see that the labels still get their address properly assigned, but they no longer change the address. And so with that, we already have support for label definitions in the program. And now instead of jumping ahead by 18 bytes here at this relative jump, we want to be able to jump to one of these labels. And this shouldn't change the output binary, but it makes the source text a lot more readable and maintainable. Let's see what happens if we run the assembler on this. So it rightfully complains that the string add isn't a base 10 integer. However, now that we have the ability to specify labels in a program, I think we want to go and change the relative jump to no longer accept an immediate operand, but we want a new kind of offset operand that can be either a label or an integer. So we need to define how these offsets are supposed to be parsed. Let me add that below the immediate integer parsing. We want to accept anything that looks like either an integer for a relative jump offset as a number or a label, and then we would go and compute the jump offset in the assembler. Until now, the relative jump offsets could be just any kind of integer with an optional leading plus or minus sign to indicate the direction of the jump, whereas the plus was basically just for cosmetics. It didn't really change the meaning of the number. So let's accept anything that starts with a plus or minus and then looks like a number or a label. So first up, let's try to see if this is an integer, and let's again support the different bases that we have supported for the immediates. And so after this matching, if base is not none, this is actually a valid integer which we can parse and then return as an operand. And at this point, if we didn't return in the if calls above, this wasn't an integer, and what we're stuck with is probably a label. And so let's create a new operand kind, and let's call it offset, and then let's store the label text in there. And one thing that can happen is that we parse a plus or minus sign followed by a label name, but that is actually not really a valid input. We don't know what to do with that. So let's catch that case if we didn't parse an integer, but there is still a sign present. Let's just print an error. Now we have to go define this operand kind, and we also have to define this offset class here. For now, the offset class only has a name field that we populate with the name of the label that we found, but we'll add more fields here as we need. So let's see if this already does something when we run the assembler. So it seems to be doing something. We get an error message, and then the Python code seems to crash here when we're trying to compute some target address. So it looks like this happens when we're printing the relative jump offset, and we're trying to compute the target address to add as a comment behind the jump relative instruction. Let me comment this out for now, and then we'll get back to it later when we have full label support here. Okay, so the assembler is complaining about something probably during the encoding where it expects an immediate offset, but we provided a label offset. But it's strange that we don't see the label printed here after the instruction. So there's probably something missing in the operand printing. And yeah, we handle a few of the operands, but in case we don't know what to do with an operand, we just don't print anything, which is pretty bad. So let's print at least something in here. So let's follow the pattern we use for instructions. When we don't quite know how to print the operand, we'll just print the Python object for now. And that works. Instead of seeing nothing, we see the Python representation for this offset operand. But let's actually print the label name for these offset operands. There we go, that prints the instructions quite nicely. And so now we need to figure out how we're going to handle relative chumps that have a label operand instead of an immediate operand. And I think a good way for us to deal with this is to add an offset field to this offset class where we can actually fill in the computed chump offset for the label that is presented there. And then we'll just make the relative chump use that value in its encoding. And then we can figure out how we actually compute that offset later. We want this to be an optional int because initially we don't know what the offset is, but for now to have something that we can actually encode in the instruction, let's just set it to 42 because that will be easily visible in the output. And now when we encode a relative chump instruction, let's use this offset. So the relative chump calls encode SM8 to encode a signed 8-bit immediate, and that in turn calls check immediate and then encode bits to encode the actual value of the immediate. And I think we can change this around slightly to have this check immediate not only consider immediate operands, but also the offset operands and the actual value that is in there. Right here we're complaining if we see something that is not an immediate, which is exactly the error message that we got before. Let me change this around such that we accept immediates or offset operands and complain otherwise. And then to make using this easier, we can also return the actual immediate value that we determined from this function. And so whenever we call check immediate, we can now use its return value as the integer that we need to encode. This should now use the 42 that we filled in for the offset and encode the relative chump instruction as before. And yes, something happens. And indeed, as you can see here for the relative chump with immediate, we actually fill in the hex value for 42 as the chump offset. Now there used to be a chump target address here that we've commented out. Let me go and add that again because that was pretty useful. Let's see if this works. Pretty nice. So we're back to printing the destination address of this chump. And so now the thing we need to figure out is when we see this offset in an instruction, how do we actually compute the integer offset in the program that we need to fill in here? We have this offset object with the label name, but we somehow need to come up with the value for the offset field. Down here, where we're actually going through the different phases of the assembler, right after laying out the instructions in the program, which is when we know what the addresses of the instructions are, I think we want to go through the program again, and for all the offset operands, we want to actually go and compute what the chump offset has to be, because we now have concrete instruction addresses to work with. I think I'm going to call this the evaluator, because in the future we'll likely also want to evaluate expressions such as addition, subtraction, and other kinds of things here. And we'll use a similar pattern as in all the other utility classes that we've created. We're going to go through all the instructions in the program and evaluate instructions individually, and then for each instruction we're going to go through all the operands, and if we find an offset operand, we're going to compute its address. So we somehow need to figure out what the address of the label is here. And then we subtract from that the current instruction address. And this gives us a relative chump offset relative to the instruction we're in. So at this point, we need to know what label the offset refers to. And I think I want to have this offset operand point to the label directive that actually defines the label that it refers to by name. And that label directive will have its address set properly because it's just another instruction that has been laid out in the program. And so initially when we create this offset object, only the name will be set. It will be the name of the label that we want to refer to. And then we need to do something after we've parsed the full program to actually go in and resolve that name and make it point to the instruction, the label directive that actually defines that label. And that's what we'll fill in into this binding. Right now this won't work because we're not setting this binding field anywhere. And again, down here, when we go through the steps of the assembler, I think what we want to do is right after parsing the input assembly, we want to go through the program again and resolve all the label names. Basically, whenever we see an offset operand that refers to a label, we want to go and figure out what this binding field needs to be and basically dig up what label that this points to. And again, later on, this will also handle names in expressions, not just the simple labels that we have today. To do this resolution, we'll have to go through the program twice. First, we need to go through the program and register all the labels in the program. And then we want to go through the program again and resolve all the labels in offset operands against this list of labels that we've collected. For the first part, we'll iterate through all the instructions in the program, and whenever we see a label directive, we'll just register that label and store it in some lookup table. And we also track an instruction index such that we can reason about the order of instructions in the program. First, let me dig up the label name, and then let's store the current instruction in a dictionary for this given label. This will later allow us to look at this labels dictionary, give it a label, and then we'll get the instruction back that corresponds to this label. And now we'll also want to check if the label isn't already defined, because we don't want to allow duplicate label definitions. Another thing we want to do here is we want to have some special treatment for labels that consist only of numbers. These are usually called relative labels, and we'll add some examples into the test program. But for now, if the label just consists of digits, let's add this to a set of relative labels, and we'll keep multiple of those around. And when we store these relative labels, it's actually important for us to also store the instruction index where in the program that label was defined. Because later on, when we resolve the label, we want to pick the closest definition of this label, closest to the jump instruction. Alright, in theory, this should now register all the labels in the program. So up here, after we've made the pass through the program, we should be able to just print out what the dictionary of labels and relative labels is. Let's see what this does. So we fail in instruction evaluation because we haven't set this binding yet. But up here you can see that we have a add label, which points to that label directive. And we have start, which also points to that label directive. And then we have a definition of the one label. It's the 10th instruction in the program, and it points to the instruction that defines it. And so if we count down from the top here, this is the 10th instruction in the program, and it indeed is this label 1. Let me add another 1 label. And when I run the assembler again, we now have 2 labels associated with the label name 1. One of them is the 7th instruction, and the other one is the 11th instruction in the program, which correspond to the 2 label definitions that we have. So that seems to work. Let's go through the program again and resolve each instruction individually. And to resolve an instruction, we basically go through all its operands and then we resolve the offset operands. And so here we'll have to resolve the label name that the user typed down as part of this offset operand. Let's start with the regular labels, they're pretty easy. We'll just look up the label name in the dictionary and then use the directive instruction as a binding. And if that doesn't work, we'll just print an error. Let's see what this does. Pretty cool. We actually go and look up what the directive is that defines this add. This returns this pseudo instruction here. We use the address for that instruction, which we already know at that point, and we compute the relative distance to the jump instruction. And this then gets inserted here at the top as a jump offset. And then we print the destination address properly again. Pretty cool, that is working. Let me quickly try with a label that doesn't exist. So this prints a nice error message for the label name. Now let me try to use a relative label. With the suffix F for forward, we expect this to resolve to the next instance of the label 1. And with the B suffix for backwards, we expect this to resolve to the previous instance of the label 1. Currently this doesn't work because we just tried to resolve the label name, but we can be a bit more clever here to do the right thing for relative labels. So relative labels just consist of digits followed by the letter B or the letter F. So let's use a regular expression to try and match that. So first let's look up the relative label with those digits. And then depending on whether we use the F suffix or the B suffix, we want to go through the list of defined labels and we want to find the first before or the first after the current instruction. And if we arrive here, we haven't found any label that matches the criteria, so maybe there's no more label with this name after or before the instruction. So we'll want to print a corresponding error, also mentioning which side we were looking for and couldn't find the label. Let's see if this works. That looks promising. And yeah, this looks pretty good. The 1F resolved to hex address 20, which is this one down here. And the 1B resolved to hex address E, which is the one up here. And these relative labels here with just digits, they're really useful for loops and if conditions that you have locally in your program. Because depending on how you generate them, if you have macros in the assembler, you might actually copy-paste multiple instances of those. And you don't want to be bothered to come up with label names that are unique globally across your entire program. Sometimes you just want to locally jump back a few instructions. And these labels, they allow you to do that. Let me also quickly try to refer to a label that doesn't exist. And that looks pretty nice. I just noticed that the backwards resolution probably doesn't quite work. Let's see which of the ones this refers to. Yep, that's what I thought. It actually picks the first label in the program instead of the last one that is just before the instruction. So to fix this, I think when we go backwards, we want to look through the labels in reverse and then pick the first one that comes up that is before the current instruction. That looks a lot better. We're referring to this one and not this one. Nice. Let me add a comment here mentioning where we expect these to jump to. And one thing we should be able to do is down here, when we are in this loop, we should be able to replace this -32 jump offset with an actual label that keeps us in the loop. So we'll add a loop label up here, and then just mention that label down here in the relative jump. And when we assemble this, this hasn't changed. We're still jumping back to address F040, which is up here at the beginning of the loop, but we now did it with a label, which is a lot more convenient than the manual computation of the jump offset. Now I think we can do a similar thing in the flags test program, where we also had this loop. And so instead of commenting out this loop label up here, we can actually uncomment it because this is now supported. And then here, we can actually just note the loop label. This looks pretty good. We have a jump to the loop now, and it's jumping back to address hex 62, which is indeed the beginning of the loop here. And similarly in the shift test program, we have this ping pong pattern here at the bottom, and we can also insert a loop here. Looks like we still have some old negation instructions in there. Let me fix those. And this compiles properly. And we have a nice loop down here that jumps back to the beginning just after the loop label. So that's pretty cool. That's what I wanted to tackle today. So we can now use these labels in chump relative instructions. We can still use the actual immediate values, integers, for the actual chump offset. But the labels make it a lot more convenient and less brittle to write these programs. Next up in this whole assembler coding, I think what we want to be able to do is use the labels as immediate values also in load immediate instructions, not just in chumps. And we probably also want to have ways of isolating the upper 8 bits and the lower 8 bits of these program addresses, computing offsets manually, getting the current program counter address at a specific instruction, etc. So this all sounds like what we want is some generalized expression evaluation support in the assembler that can compute certain offsets very conveniently. And then the whole chump offsets being labels could just come out of that work as a nice side effect. But that's something for the next time. For now, this looks pretty good. The labels are going to be very convenient in the future when we write more complicated programs. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.